Hey YouTube, this is my first video in a series that I'm doing on solving trigonometric equations, and in this video we're going to go through some basic notation, some basic steps, some things that we like to carry out, as well as interpretation of our results, okay, and how many results we actually get when you solve a trigonometric equation. So we're going to go ahead and start by considering a very simple equation, that is sine of x equals a half, where x is our angle. And what I want to kind of indicate here is, first of all, we are solving for angles that would make this statement true, okay. So when we are solving a trigonometric equation, sometimes it is actually beneficial to say, let's go look at the solutions of this on a graph. And so what I've done is I pulled up Desmos here, as a matter of fact. You can see that I've got my x-axis set up in increments of pi halves, and we will graph the graph of y equals sine of x. So I've got y equals the sine of x, which is our familiar graph here. We say that is a graph that has a period of 2 pi and an amplitude of 1. Okay. What we want to know is, essentially this: what angle or what x values would have to be on this graph such that the y value comes out to be a half. So what we can actually do is we can go graph y equals 1 divided by 2, and you can see this purple line here that intersects our original graph at all of these x values. And so what we want to do is we want to basically figure out on an interval from 0 to 2 pi, what are all of the x values for which our graph is at a height of a half. And so we can actually just click on these two intersection points right here. And what we can see is we get a couple of ordered pairs, and at least on this interval from 0 to 2 pi, we can see that there are two x values here and here, or two angles here and here, for which our graph is at a height of a half. We can see that the output here would be a half at these two input values, pi 6 and 5 pi 6. And of course, that certainly makes sense. If you took the sine of pi 6, the sine of pi 6 is a half, and the sine of 5 pi 6 is also a half. This can also, by the way, just be verified just by looking at your unit circle, but we're saying on the interval from 0 to 2 pi, what are two values in this particular instance where our sine value is equal to a half? And again, you can see here a pi 6 rotation would give us a y value of a half, or a sine value of a half, and also a 5 pi 6 rotation here would also get us a sine value of a half. And notice that both of these angles, by the way, have reference angles that are 30 degrees. Of course, we know that anytime you take the sine of 30 or the sine of a pi 6th reference angle, you get a half for a value. It's just that it came out to be a positive half in the first quadrant because sine values are positive over here. All students take calculus. Also this, it came out to be a positive half in the second quadrant just because it has a 30-degree reference angle, but it terminates in the second quadrant, and sine values are positive over here. We can see that we have positive y values. This is going to be our goal in this video, is to ask this question. Essentially, what are all the angles that would make this statement true? The thing here is essentially this. When I go back and look at this graph, however, you will see that these are not the only two locations for which our graph is at a height of an output of a half, okay? We can see that also at, say, 13 pi 6th and 17 pi 6th, we are at a height of a half. And if we deviate over here to the left, we say negative 7 pi 6 and negative 11 pi 6. As a matter of fact, if I were to zoom out here, we could say that, speculate how many x values or angles exist for which our graph has an output, or a sine has an output of a half, and we could say infinitely many, okay? So, noting that, let's go back over to our canvas here, and we'll talk about how I would necessarily solve an equation like this, and then interpret our results. But first things first, when you solve a trigonometric equation, we are trying to isolate this x value here, and currently the x value, or the angle in this particular instance, is buried inside of a trig function. So step number one is always going to be this: when solving a trigonometric equation, we're going to isolate the trig function. That is, I don't see like a +1 on the side here. I don't see like a 2 times sign in front. We've got sine of x equals a half. Once we've done this, though, we are going to undo our sine function using the inverse sine function. And so we'll write it like this. We'll do the inverse to both sides. Where we had on the left side, we had a sine of x, okay? And on the right side, we had a half. And what we know about the properties of inverse trig functions, or inverse functions in general, is that they undo one another and get us back to the original input, which is this angle. So we can say, first things first, when you solve a trig equation, it is entirely appropriate to write things thusly. This right here is the set of all possible answers that exist. We say this angle is the angle that exists, that when you take the sine of it, you get a half for an output. Okay? So when we talk about what angles give me a half for an output, this is where we would either go refer to your unit circle or use your common knowledge of sine values here. But we say sine would be a half if we had a pi 6th reference angle here. So we say there are two angles on the interval from 0 to 2 pi that give us an output of a half. That's pi 6th and 5 pi 6th. What I'm going to do is just say this right here. We would say that x prime, or sometimes we write x party hat, this is a reference angle here. We'd say that this is a pi 6th reference angle, okay? Once we've determined, though, the reference angle, what we're really going to do is we're going to try to sketch out what are the two angles in the xy coordinate plane on the interval from 0 to 2 pi that would give us a sine value of a half. And knowing what we know about the values of trig functions in these four quadrants, we say all students take calculus. We know that sine came out to be a half and has a pi 6 reference angle, but it came out to be a positive a half. So as far as where this angle could not terminate, it couldn't be the third quadrant, it couldn't be the fourth quadrant because sine is positive. So what we're going to do is we're going to go sketch a couple of pi 6 reference angles. We say that this would be pi 6 here actually. And then we say, okay, we'll sketch a pi 6 reference angle over here. Now, just because this is a pi 6 reference angle doesn't mean that's the actual angle. We're asking for what are these angles in standard position. So we say one of our solution values is at pi 6, and then the other solution value, I'm going to kind of squeeze it in here, between 0 and 2 pi, is this angle here. We'll call it phi maybe. Actually, we say that these are actually supposed to be x's, so let me go back and switch this. The angle x could have been pi 6, or it could have been a pi 6 short of 6 pi 6, which is 5 pi 6. So there are two solutions on the interval from 0 to 2 pi for this equation. We say that x is either pi 6 or it's 5 pi 6. Okay. So now, these are the solutions that exist if this is true. If we say that x is somewhere between 0 up to but not including 2 pi. There are often times where we want to find infinitely many solutions to this equation, and we knew that infinitely many solutions existed on this graph here. For instance, 13 pi 6 and 17 pi 6. So the real question is, well, how would I have determined these? And this is pretty simple. As a matter of fact, all we need to do is acknowledge that this graph just repeats over the length of a period length here, whatever its period is. In this particular instance, we say, well, the period of this graph is 2 pi. So the idea here is this. If we were to take pi 6 and add on 2 pi to this, we would get 13 pi 6. And this can be shown easily. We would say pi 6. If you were to add on its period length, we would get pi 6 plus 2 pi, or pi 6 plus 2 pi over 1, or pi 6 plus getting a common denominator here, we get 12 pi 6. So this is our 13 pi 6. And the same thing can be shown if we were to have taken this 5 pi 6 and added on a 2 pi to it. As a matter of fact, we say anytime you add on or subtract off a multiple of 2 pi, you will just land back in a spot where this is also true because this is a periodic function. So the idea here is going to be this. When you solve a trig equation, you isolate the trig function, undo it with an inverse trig function, and then we seek to answer this question. What are the angles between 0 and 2 pi? What are the angles on just one full rotation interval for which sine came out to be positive a half? And once we recognize the reference angle here, we're able to construct which quadrants it terminated in with the respective reference angles here, and then ask ourselves, well, what are these actual angles in standard position, which we got pi 6 and 5 pi 6. So the only other thing we need to do here is if we are seeking all possible answers for this trig equation, what we need to do is we need to add on, in this case, 2 pi n, where n is an integer. And what I'm going to do is I'm basically going to make this comment. I'm going to say, really what we were adding on was the period times n. Period times n. Okay. And the reason why is because this graph will repeat every length of its period. So when we list answers to such trigonometric equations, if you are not only being asked for answers on the interval from 0 to 2 pi, and you have to include all possible answers, we'll just add on multiples of the period to the 2 answers or 3 answers or 1 answer or however many answers you got, or maybe no answers. Cheers.